Hi, my name is Ying Wang. Today I'm going to talk about porting to the web. That is, porting native applications or libraries to the web using a nice tool called Inscriptum. So, why do we need Inscriptum? Comparing to native development environments, the web has fewer libraries, fewer tools, and even fewer developers. To catch up on those advantages of native development environments, it requires enormous time and money. Performance on the web is also a problem that has always been the most concern when running resource-demanding programs, such as 3D games. Hence, the demands of the technologies that can bridge the web and existing native libraries and applications become more desirable. In the following presentation, Inscriptum, a tool which solves this issue, will be introduced. With Inscriptum, the developing of those high-end 3D games on web will be easier and more cost-effectively than ever. Furthermore, with the pursuit of open web, the technologies of Inscriptum are either standard-based or aiming at standards. In those days, when it comes to web, one may only think of pages, usually a static and flat presentation composed by text, pictures, forms, and buttons. That's pretty much it. As you can see today, the modern web looks very different. Not only it becomes prettier and fancier, also becomes more interactive with the emphasis of scripting. For example, we have WebGL for 3D graphics. We have WebWalker for multi-threading. We have geolocation API for navigation, and we have IndexedDB and file system API for data storage. The web becomes a very versatile platform which is available to everyone nowadays. No matter you are using a PC or a mobile phone, no matter your device is running a Windows, a Linux, Android, or iOS. It's the cross-platform web that matters, not the operating systems anymore. On the other hand, there are a great number of libraries, frameworks, and applications written in other languages. Development tools have been evolving for those languages for a long time, not to mention the larger user base of those languages, especially C and C++. Try imagining the consumption of time, efforts, and most importantly, the cost of rewriting a commercial 3D game engine such as Unity. Even rewriting a mid-sized library such as like JPEG or SQLite can cost you a considerable long time. That you have to not only rewrite the codes, you have also to test them and tune its performance in order to achieve the same quality to the existing stuff. Performance is another advantage of C and C++ programs, since they are statically typed and lack many of the high-level semantics in JavaScript. They can be compiled and executed more efficiently. Most advantages can be reserved even when they are compiled into JavaScript if we treat them carefully. So, as for porting to the web, we are actually talking about compiling to JavaScript, or more precisely, compiling other languages in the native development environments into JavaScript on the web. In fact, JavaScript is not the first project that realized this idea. You may already know that Adobe's Flash CC compiles C++ into ActionScript, which is a cousin of JavaScript, or Google Web Toolkit, which translates Java into JavaScript. When I first heard about those projects, my first idea was they must be crazy, and there must be a considerable slowdown, maybe 10 times to 100 times. Since they are running low-level and detailed languages on high-level ones, kind of like emulators. I have seen some similar technologies in the opposite direction. That is, to compare those high-level dynamic languages into low-level ones for performance, but not vice versa. At first, I thought they are counterintuitive and should be proof of concept projects and have no practical uses. Well, it turns out to be practical. Thanks to the rise of JavaScript engines and the ingenious designs, it's fast enough. More precisely, its running time costs less than double comparing to the native ones. Or we can say only a 50% slowdown. Okay, to see is to believe. Let's take a look at a demo. This is Unreal Engine 3, developed by Epic Games. It's written in C++ and it's running on many platforms such as Windows, OS X, Linux, PlayStation 3, Android, and iOS. It's composed of about 1 million lines of code and got ported in just 1 week. Now it's running smoothly on my laptop with a built-in Intel graphics chip sold in 2011, which is definitely not a powerful fit. The same computing power is available on most new computers and even old computers with an additional graphic card. As you can see, the CPU usage is quite recent. It's not very high. Okay. The Inscription project is initially and mainly developed by Dr. Alon Sakai in 2010. It's basically a compiler that compiles LLVM bitcodes into JavaScript. You may also regard it as an LLVM backend, although it is not written in JavaScript. It is written in JavaScript and does not link against LLVM directly. The process of compiling C or C++ source code into JavaScript is, first, compile the C++ source using CLang, which is an LLVM front end, into LLVM bitcodes. Then, several LLVM optimization passes are applied on the bitcodes. Finally, Inscription compile the LLVM bitcodes and emits JavaScript. Some additional passes may be applied after Inscription, such as Google's closure to minify and obfuscate the resulting JavaScript code. Scripton also provides standard library for C and C++. Other important libraries such as SDL, OpenGL, and EGL are also implemented. There are also some useful scripts provided by Scripton. For example, EMCC can be used to compile C and C++ source codes into JavaScript at once. It's designed to be used in a way similar to GCC. There are also configure and make alternatives called emconfigure and emmake, respectively. That will be covered later. Before showing the example, let's look at Scripton more closely. Since JavaScript has no direct access to raw memories, how does Scripton implement the memory operations? For example, an indirect access via pointer in C. The other problem is that C and C++, or more correctly, LLVM big code, are statically typed, while JavaScript is a dynamic typed language. How do we describe the precise behavior by the relatively imprecise language? The answer to the first question is typed array. A large array buffer is allocated before the main function as the C and C++ heap. Every memory operations in the source language eventually get mapped into this array buffer. For each type array provides a corresponding view. A 4 bytes long memory block can be treated as one signed 32 bits long integer, or as 4 unsigned characters. Like native compilers, Scripton treats the memory address or pointers as integers. All the memory addresses in LLVM big codes are used as offsets to heap. That is, the offset to a large unified array buffer. For the second question, let's recall the spec of JavaScript. The spec says that values in JavaScript are limited to certain types in some situations. For example, bitwise operations are integer only. So a 32 bits long integer can be obtained by ORing a number with 0. The first example shows a typical integer arithmetic generated by Scripton. The second example shows how a memory and load the second example shows how a memory load of a 32 bits long integer is done. Let's look at a hello world example. In the lower left corner, we can see how EMCC can be used in command line. Just like GCC, most of the time we only care about the input source and the output codes. Seems like there is only one step of compilation. The details of the whole process are hidden. After the compilation, you can execute the resulting JavaScript codes by a JavaScript shell, such as Rhino or Node.js. We next look at some details. Recall that C pointers are implemented as offsets to heap, which is the unified large typed array. Before the main function, the space is reserved, and the string hello is stored to heap. The parameter passed to puts is the offset to heap, namely the C pointer or memory address of the string hello. Allow me to show one more example. The function is compiled by Scripton from a common function in standard C library. string length to calculate the length of the string. You may already note that parameter PTR is first ORed with 0 to be sure that it's an integer, more precisely a pointer. The variable current used as the iterator is also a pointer. The expression in the condition of the while statement shows a typical memory load of characters. We have seen two examples that show how the semantics of source languages are carried out by JavaScript. Now let's turn to performance. Scripting is designed to emit low-level codes that high-level facilities of JavaScript are avoided. For example, there's no objects and hence properties because places are inherently expensive due to their dynamic nature. Allowing defining or altering places at runtime makes the follow-up operations, such as to read or to write the properties, not optimizable. They may need table lookups or even traversals in the graph hierarchy. Scripting also tries to emit codes which are statically typed. Modern JavaScript engines perform type inference or type profiling. They try hard to specialize the code. Once success, most of the type checking, boxing, and unboxing and even overflow checks can be eliminated, while there are still some guard code needed. The codes emitted by Scripting is much more predictable and optimizable in this way. It makes JavaScript engines more efficient. Most of the garbage collections are also eliminated because there is no objects and most of the memory operations are done in the unified type array. Scripting doesn't use strings and arrays. It only relies on numbers, functions, and local variables. Another benefit come from LLVM's optimization passes. Some of the expensive analysis and optimizations that are impractical for JIT compilers, such as inter-procedure optimizations, or some global optimizations, can now be applied in Scripting without adding any overhead to runtime. It's also benefited from one of the code designs called ASM.js. ASM.js is a specification. It defines an extraordinary optimizable low-level subset of JavaScript. It's fully compatible to standard JavaScript since it's only a subset. That is, codes conforming to ASM.js will behave exactly the same on browsers supporting JavaScript, supporting ASM.js or not. The advantages of performance come from this contract. When using ASM in front of ASM.js code, the underlying JavaScript engine can optimize it much more aggressively. Verifications will be done, of course. Runtime type checks, boxing, and unboxing can be eliminated completely. The optimized and specialized code will always be valid according to the contract. No type guards and hence the optimizations are needed. It also allows ahead of time compilation, making offline caching more feasible. By the way, many cases shows that it often runs faster than JavaScript codes, which is rewritten by human from C or C++. Mozilla already have a working JavaScript engine that recognizes ASM.js. Experiments show that the running time of JavaScript code compiled from C and C++ costs no more than double comparing to the native, or we can say only 50% slowdown. This is quite feasible for most 3D games which are GPU bounded. Moreover, it's developed by only one engineer in 1 month. Now it's still improving and more engineers are getting involved. It has great potential. By the way, it's enabled by default in Firefox 22, which was released 3 days ago, I think. Well, there are still some limitations. The first is multi-threading. Web worker is somewhat limited. It can't share states or variables that have no ways to deal with synchronizations. The only possible communication is by asynchronous message passing between the main thread and its worker, not even possible between the workers themselves. Major synchronization mechanisms such as locks, mutex, semaphores, or monitors are impossible to be implemented. The second is local event loops. Due to the event model of client-side JavaScript, the codes compiled for browsers can't contain a never-end custom event loop. Every function in client-side JavaScript must return in a reasonably short time. It's kind of like doing time slicing on our own. But don't worry, every client-side JavaScript code does this, and computation-intensive codes can be uploaded to workers. Also, there's no efficient ways to implement MMU-related functions like mmap. This is because there's no standard API exposing the capability of MMU to client-side JavaScript. Currently, Inscription implements mmap by loading all the contents into memory at once. The non-portable codes, of course, can be compiled and executed off-box. For example, codes relying on indents, alignment, or even inline assembly won't work. Native state manipulation won't work either. That means set jump and long jump can't be implemented generally. However, Inscription does support a simplified version of set jump and long jump by leveraging the JavaScript's exceptions. Here are some projects using Inscription. We have already seen Unreal Engine. Banana Break is a 3D first-person shooter game. It takes the Cube 2 Cyberport engine, which is written in C++ and OpenGL. It's written to be a test case and benchmark of browsers, and also to provide that games of this nature can run in JavaScript and WebGL. Unigine is another well-known 3D game engine. Inscription Qt ports Qt to JavaScript. With it, you are able to write Qt programs on the web. LZMA.js and SQL.js are portings of LZIP and SQLite, respectively. Okay, that's it. Thanks for your listening.